Good morning. I hope you all are doing well. And I wanted to say again, thank you for all of your presentations this week. They sure were fantastic. Special thank you to the winners of the Peer Best in Show kind of thing. There were lots of people right in that area, but man, overall, these were some really outstanding presentations. Jade asked earlier about when they're going to be up online, and it should be by the end of the day. I'm hoping like noon and stuff, so I've got to check a few more things out. But again, well done, very cool. We're going to continue talking about entropy, and we're doing some review of some Chem 221 stuff mostly, but a little Chem 222 on enthalpy. Enthalpy and entropy, we're going to see, are very connected when you want to figure out if a reaction occurs or when it doesn't occur. And enthalpy is related to energy being released, energy dispersal, which is a big part of when reactions occur. When people studied all reactions that ever occur, energy dispersal was the biggest one, and enthalpy is basically a measure of that. But the other one that happens is matter dispersal, like going from a small amount of matter to a large amount of matter, and that's where entropy kicks in. So to understand some of the things of entropy, the matter dispersal, we're going to review, I guess, a little bit about the energy dispersal, the enthalpy parts. So here we go. Now on these sections, you'll need a table of values of entropy and or enthalpy. And at the end of problem set 5 is a many-paged handout, which is just a guide for all these different values. You can totally look them up on Google as well. But especially on problem set 4 at the end, there are a couple of problems where it would be nice to have that table. So if you have problem set 5 handy, you'll be good to go. Otherwise, you can, there's a website, I have a website, or you can look up on Google or whatever. So anyway, if you have a lot of the enthalpy values for reactants and products, you can figure out the overall enthalpy change by taking the sum of all the individual enthalpies of the products and subtracting the individual enthalpies of the reactants. So these little zeros right here mean standard states, all right? Standard states are the common way that you find in tables and stuff like that. And if you have the enthalpies of your products and reactants, you can calculate the overall enthalpy of the reaction. So in this reaction right here, 2 hydrogen gases are reacting with an oxygen gas to make 2 liquid water molecules. And you can see here how the process is you take the products, the water, and you subtract the reactants, which in this case are hydrogen and oxygen. The numbers you get from the table are per mole. So if you have more than 1 mole, i.e. a 2 right there and a 2 right there, make sure you incorporate those in the products minus reactants parts. So you'll see here there's a 2 in front of the liquid water, and there's a 2 in front of the hydrogen, but there's just a 1 in front of the oxygen. Now in this problem, in Chem 221, we talked about how the elements in their standard states have enthalpies of 0. So that would be things like hydrogen gas, oxygen gas, iron as a solid, because that's its natural form, mercury as a liquid. So if you look up those values, you'll see that they're 0. All the compounds, for example, water, as well as the elements in non-standard states, like diamond, like liquid oxygen, those things will have enthalpies that aren't equal to 0. But if you see 0, that's what that means. So using the table of enthalpy values for this particular reaction, the enthalpy negative 571.70 kilojoules per mole. And if the delta H number is negative, that means it's exothermic. So there's a lot of energy being given off as hydrogen and oxygen are combined to make water. This was the reaction that the space shuttle used a lot, some of their boosters and stuff, and so there's a lot of energy released, which is pretty cool. Any questions on that? Okay, there's a corresponding entropy version of that rule. And just like with enthalpy, which was products minus reactants, the entropy will be the same thing. So we're going to now calculate the entropy of the same reaction, but the difference here is this is going to be, again, an entropy calculation, not an enthalpy. But just like with enthalpy, you take all of the entropies of the products and you subtract it from all of the entropies of the reactants. And that little sigma just means add up all of them, all right? So in this case, we have 2 reactants and 1 product. It'll be products minus all of those reactants. And again, remember to look for the entropy values. Now, when you look up values of in the table and stuff like that for entropy, all of the individual entropies should be positive numbers, all right? The third law of thermodynamics said that only those pure crystals of pure elements at 0 Kelvin, which is essentially impossible, those are the only times you're going to have values that are 0. And individual entropy values should not be negative either. They'll always be positive numbers. So in this case, water's entropy is this number. We're going to multiply it by 2, just like we did with enthalpy. And we'll subtract from it 2 times the hydrogen plus 1 times the oxygen. And again, notice how the gases have bigger entropy values than the liquid water does. We talked about how gases have the most entropy, liquids are less than that, solids have the least amount of all. So when you do this, we have an entropy change, which is negative 326.9. And again, these numbers just come from the table, all right? They're nothing you have to memorize. While the enthalpy values were 0, the entropy values should all be positive numbers and stuff. And you can, again, look them up in the table. Now, we've talked a lot about entropy always being positive, and that's for individual compounds or elements, but you can have an entropy change which is negative. So if you look at this reaction long enough, I can think of at least 2 reasons why this reaction should have a negative entropy change. One of the reasons is we have 3 moles on the reactant side. 2 plus 1 is 3. And those 3 moles are going to 2 moles on the right side. So 3 going to 2, this is like more ordered, all right? Instead of having 3 pieces running around, now you have just 2 pieces. Entropy is all about disorder and messiness. So this is kind of like cleaning your room, all right? Yes, you can do it, but entropy isn't happy with it, all right? So that's one reason. I'm literally looking at the stoichiometries, and the final stoichiometry, total number 2, is smaller than 2 plus 1, 3 on the reactant side. That's one way to justify why this is negative. But the other thing is that entropy, as we've talked about, likes gases, and it doesn't like liquids and solids as much. So we're going here from lots of gas to a liquid. That's another reason here why entropy really isn't happy with this reaction. So those are the kind of things that will give an entropy reaction a negative number. The individual entropies will be positive, but the overall change can be negative. So, any questions on that? We did this example on Wednesday, but if you'd like to do it again, that would be totally cool. We're looking here for an entropy change for this reaction. And again, what you would do is you take the entropy S of CuO and you'd subtract the entropies of copper and half of an oxygen. And you do have to have values here. You would not be expected by any means to do this just by yourself. So copper oxide, this number, 42.59, then you would subtract, you'd subtract the copper, this number, and you'd subtract 1/2, of 205. This will come out to be a negative number, and it looks like it's negative 93.12. So again, entropy of CuO minus copper and half of an oxygen. Good to go. You can also justify why this is negative. You have 1.5 moles going to 1 mole. That's more ordered, all right? Not as much flexibility. Also, you have a gas being incorporated into a solid. And those are the kind of things that I use sometimes to justify the reasons for the values. Questions? Okay. Also, in terms of enthalpy versus entropy, The values in the tables are usually entropy of formations or formation entropies. And again, we saw this with enthalpy, all right? An enthalpy of formation had a little F next to it, and sometimes the little delta S's will have an F next to it as well. And that little F just means formation. And the formation, if you see it for enthalpy or entropy, it means two things. First of all, you can have only 1 mole of product, and the other thing is that all the reactants are going to be elements in their standard states. So sorry, I didn't do my timing here quite right. I wanted to stop it. So just pretend that's not there for a second. All right, so here's an example of a delta SF reaction, all right? And why we can justify the F part is that first of all, we have only 1 mole of product, all right? Not 2 moles like we saw earlier, but just 1 mole, all right? And the reactants, hydrogen and oxygen here, these are elements in their standard states. So it's not liquid hydrogen, it's not hydroxide, OH minus plus H plus, those wouldn't be elements. You have to have elements in their standard states. So if you see that little F, whether it's a delta H or a delta S, just realize these are the two definitions you want to follow. 1 mole of product, and all of your reactants will be elements in their standard states. So this thing right here is just an example of how you calculate it, all right? You take the water as a liquid value, and you subtract the gases to get this number right here. If you see that little F, that's what it is. And those tables of values of entropy and enthalpy, that's what they're going to be. They're going to be values of entropy. They're formation values. Okay. So let's again try and calculate this value. And you know what? This is the same problem I just did, isn't it? All right, well, I just want to make sure you got this. I think what I was planning to do was, this really is an entropy of formation. I think, oh gosh, sorry gang, you're not seeing me at my best here. I think I was trying to think about making a question about entropy of formation. Well, pie in my face later, we can know that we're all human and sorry. Anyway, imagine, sorry, questions? Thank God it's Friday. I mean, it's good that Friday is here. We can all have a chance to relax and cool. All right, sorry. All right, the next slide is actually the most important probably of all of Chem 221 and 223, so what a spaz way to go in, but that's kind of how I roll. I want to talk about rules that are used to describe when reactions occur or they don't occur. So you'll notice that so far we've talked about the first law of thermodynamics, energy can't be created or destroyed. We talked about the third law, and the only time entropy of something is 0 are those pure crystals of elements at 0 Kelvin, which is like never. This one, gang, is the reason why thermodynamics and creationism, by the way, sometimes get into a fight once in a while. But anyway, it's the second law of thermodynamics. So this is a big one, and this is going to be something we're going to talk about here. But what it says is that a reaction is spontaneous. Now remember, in my world, spontaneous doesn't mean, hey, let's go see Avengers again. It means this reaction will occur. Non-spontaneous means reactions won't occur. So you can think about a spontaneous reaction as product favored. So if you have a reaction which is going to occur, the delta S of the universe has to be positive, okay? So universe is obviously pretty big. Universe, delta S, is going to equal the delta S of the system, what you're studying, plus the delta S of the surroundings, everything around the system. And if you're going to have a product-favored system, the delta S of the universe must increase. So that doesn't seem like too cool yet and stuff like that, but bear with me, there's some really interesting applications of this. If you want to find the delta S of the universe, you have to do two things, all right? You have to calculate the delta S of the system, all right? And the delta S of the system is delta S products minus delta S reactants, the thing we saw already. And then you need to figure out the delta S of the surroundings. And we're going to see that the delta S of the surroundings is related to the delta H values we talked about earlier. And if you do those and you add them both up, if delta S of the universe, this is what's going to give the reaction thumbs up. And I really want to highlight how important this is, all right? Any reaction that you've ever done or anything that you've done as a human being, all right, you have to have a delta S of the universe which is greater than 0. Delta S of the universe has to give you thumbs up. If you tried to do something and it just wasn't going to happen, that's probably because delta S of the universe was less than 0, all right? So if you drink caffeine because you need extra power on a Friday because apparently you're low energy and your slides are messed up, all right, caffeine, thumbs up, delta S of the universe somehow is increasing. On the other hand, if you instead want to, I don't know, do cough syrup and stuff instead, well, that's probably not going to give you what you think and stuff. That's going to be a whole different set of reactions. That's probably not going to give you where you want to go if you want more energy. That would be bad. Now we're going to see how delta S of the system and delta S of the surroundings can be calculated and how you can actually figure out if a reaction is going to go or not.
My marriage, I told you, was dead for years. I don't know why. Oh, yes, I do. It's the second law of thermodynamics. Sooner or later, everything turns to shit. That's my phrasing, not the encyclopedia.
This is from Husbands and Wives, and she said that basically, second law of thermodynamics, everything turns to S in my G-rated class. Sorry for the bad word, everybody. I hope your ears aren't bleeding. Anyway, one way of thinking about this law is that everything does turn to S, all right, because entropy is disorder, all right? And you're going to end up at the end of all product-favored reactions of either the system and or the surroundings more messy, all right? And S, sorry for all these acronyms and stuff like that, human waste. S is not as cool as the pizza that goes into it, shall we say. So this is why she said it, and that's why a lot of times people think that in some ways the entropy of the universe, because it's has to be greater than 0, everything is being turned into a more disordered state.
When we dissolve ammonium nitrate in water, the dissolution is an endothermic process. The temperature of the solution decreases over the course of the reaction. The reaction, though not favored energetically, is favored by entropy. It is said to be entropy-driven. As the ammonium nitrate dissolves, the entropy of the system increases. At the same time, the surroundings lose energy and experience a decrease in entropy. The increase in system entropy, however, is greater than the decrease in the surroundings entropy. Thus, the total entropy, the sum of the entropy changes in the system and surroundings, increases as demanded by the second law of thermodynamics.
At the beginning of this section, we talked about how in Chem 221 and Chem 222, most of the time enthalpy was like our measure stick to if a reaction occurs or if it doesn't occur. And so in that case, exothermic reactions are usually the ones that are product favored. Those are the ones that are going to go. However, this was an example of a reaction, although not very exciting. You put solid ammonium nitrate in water and you get it dissolved on its own, all right? This was an example of a reaction that was endothermic, all right? The temperature actually went down. If the temperature goes down, energy is going from the outside in. So this reaction in Chem 221 and Chem 222 would have said, oh, this isn't going to happen. But as you saw in the video, you stir it up and it dissolves. And that is something happening, all right? That's a thumbs up from the delta S of the universe. So what we can do then is analyze this reaction for both the delta S of the system and the delta S of the surroundings, and hopefully our delta S of the universe will be a number larger than 0. So what we're going to do is go through an example of this, first of all for that water example that I've been buzzing you with this morning. So what we need to do, if we're going to do the second law of thermodynamics, is we first need to calculate the delta S of the system and the delta S of the surroundings for this reaction. Then we'll add them together to give a delta S of the universe value. Now, earlier today, we saw how the delta S, which was the products minus reactants, so 2 waters minus 2 H2 and an O2, that delta S number was negative 326.9. all right? It was entropy disfavored. We had 3 moles of gas going to 2 moles of liquid. None of those things are happy. So the delta S of the system is quite negative. Now, you can relate the delta S of the surroundings to the delta H of the system, all right? We're going to see how this plays out later. And so you can do the same kind of reaction here for a delta H using this reaction right here. So again, to figure out the value, you would go and look up 2 delta H formations for water and subtract the delta H of the hydrogens and oxygen. And when we did that number earlier, which was at the very beginning of this lecture, that's where this negative 571.70 came from. So the first slide I showed, it was delta H of products minus delta H of reactants. That's this number right here. Now, if we're going to turn this into a delta S of the surroundings, there's 2 things we need to do. First of all, we need to convert by multiplying delta H by -1 and dividing by the Kelvin temperature. And this little 0 thing right here means standard states, which is 298. But the other thing we need to do is that usually entropy is just in joules. And delta H, which usually has a larger magnitude, is usually in kilojoules. When you look at the column of delta S and delta H values, the S is in joules and the H is in kilojoules. And when you do all of this, you get this number for the delta S of the surroundings. So again, we're trying to get the delta S of the universe. That equals delta S system plus delta S of surroundings. System was just entropy of products minus entropy of reactants. And to find delta S of the surroundings, we first found enthalpy, product enthalpies minus reactant enthalpies, and then converted it over to get this number. So if you take this number and this number and add them together, you can see if this reaction is going to occur or not. So again, those 2 values are these numbers right here from the last slide. We're going to add them together to give the overall delta S of the universe. But before we go on to the next slide, or you look at the remainder of this page, this is making water. Do you think this reaction is going to occur or not going to occur? Going to occur. Yeah, I see some thumbs up. Well done. Water likes to be made. All right, our planet, fortunately, is filled with water. If something's going to happen, if you give it a thumbs up, will the delta S of the universe be a positive number or a negative number? Positive, right on. So we hope, as denizens of this planet with lots of water, that the delta S of the universe will be positive. It is, woohoo! So water should form, all right? That's good because there's a lot of water around us, all right? This number here is quite positive. Water really wants to form, and that's a cool thing.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light. In the combustion of hydrogen and oxygen, the entropy of the atoms in the sample, or system, decreases. This decrease occurs in concert with the transfer of thermal energy to the surroundings, leading to an increase in the entropy of the surroundings. The entropy increase for the surroundings is greater than the decrease for the sample, so the net change in entropy is upward.
So in this little darker purple circle, this is where the system is happening. And the system is literally reactants going to products, all right? H2 and O2 making water. And the system really doesn't like this reaction. That's where you have the 3 moles of reactant going to 2 moles of product. That's getting more order, all right? More pieces, more disorder. This is going to less pieces. That's not cool. And the other thing is that you've got lots of gases going to liquids. Gases have higher entropy than the liquids. The system is very entropy disfavored. It doesn't like this reaction. But why this reaction occurs, and that's good for us as people that use a lot of water in our bodies, obviously, why it occurs is that the chaos in the surroundings, it's like the light purple region and beyond, all right? The chaos in the surroundings is quite great. The energy that's released and stuff makes all these molecules like go kind of crazy. If there was any order to them before, they would be less ordered than they were. So it's the surroundings here which kind of make this reaction occur. So the universe says thumbs up, all right, even despite the system here not being real happy with what's going on. So which of these do you think would have the largest positive entropy change? Now again, remember, entropy is all about disorder, and we've been babbling, I've been babbling, let's be honest. We've all been babbling about things and stuff that make entropy values go higher and smaller, all right? So as an example, do you think it's reasonable that a gas going to a liquid would have a positive entropy value? No, that's right. Gases are the most highest entropy of all, and liquids are kind of in the middle, and solids have the least. So gases going to liquids, as well as liquids going to solids, those will both be decreases in entropy, and that one shouldn't have any effect, all right? That would be a negative entropy change, because you're going from a higher entropy state to a lower entropy state. Now, this one right here is kind of interesting. You've got gases on both sides, all right? But notice how you have 2 moles of gas here, and 1 + 1, 2 moles of gas right there. Now, this one would be pretty close to 0, I would argue, because the state is the same, gases on both sides, all right? You have 2 moles on the left, 2 moles on the right, so the moles are the same. There might be some slight differences, but I don't think it would be very big, if nothing else. But this one right here, if you look at it, all right, 15 halves is 7.5, all right? 16 over 2 would be 8, so a little less than that, 7.5. So you have 7.5 moles of gas and 1 mole of liquid, making 9 moles of gas. So if you look at that one long enough, first of all, you have more moles on the product side than you have the reactant side. This would be 7.5 + 1, 8.5 moles total, and this is 9, that's a little bit more. And also, all the moles on the product side are gaseous. This one's actually a liquid, so that would be lower entropy. So I would say that C would be the best guess here for the largest positive entropy change. This one would be around 0, maybe a little positive, maybe a little bit negative, I'm not sure, honestly. But this one right here should definitely have a positive entropy change. Questions? So, this is an interesting thing, because now we can begin to predict if a reaction is going to occur or not, all right? You've got a CRISPR process, and you're adding some stuff in. If you had the different values for the process, the delta H and the delta S, you could actually plug these in to see if the delta S of the universe is happening. Let's say that you have an iron complex and you want to add some cyanide to it, and that's something that sometimes happens. If you have delta S of the universe, or delta S of the surroundings and delta S of the system, you can figure it out. There's basically 4 possibilities that are rubbed out of here, and I'll be honest, we're going to look at a different system in a little bit, but this is kind of laying the groundwork for what we are going to do. If you have an exothermic and a greater disorder, then you're always going to have a spontaneous reaction. And again, spontaneous is just another way to say that delta S of the universe is larger than 0. But you can also have here an endothermic and a more ordered system, and that's going to create something which isn't going to be spontaneous under any conditions. So this one will always happen, this one will never happen, arguably, and the middle two are going to depend on temperature. Now we're going to look at a different system here, because sometimes delta S of the surroundings is weird. It's proportional to negative delta H, which is awkward, so I'll show you a different system here in a little bit. But we're getting up to the point now where you too can say, give thumbs up and thumbs down, all right? You calculate delta AS and convert it to delta S surroundings and find delta surroundings system, you can then find out if the delta S of the universe is positive. And positive delta S of the universes will occur. On the other hand, if it's negative delta S of the universe, you'd say it's not spontaneous, not going to happen. So reactions obviously are important, and everyone is different. So, oh, what is this? So you probably never thought that chemistry was that much fun, but anyway, this is just showing the importance of reactions. This was actually a promotion for a European chemistry lab. They wanted to bring people in and stuff, but it cracked me up. Anyway, the full link is on YouTube. All right, let's move on. So, Gibbs looked at the weird delta S of the surroundings, and he thought, man, this is really lame. And by the way, Gibbs is arguably the first American with a PhD in chemistry. So, woohoo, Gibbs, go. Him and Lewis of Lewis Structures and Lewis Acids Bases are seen as the two really first American chemist PhDs, whatever. He thought, wow, this really sucks. I mean, negative delta H over T, that's really awkward. So what Gibbs did is he multiplied the entire equation through by negative T, all right? And by doing that, negative T times negative 1 over T, they cancel out and you get just delta H. You end up with negative T times delta S of the system, and then you end up on the other side with negative T times delta S of the universe. And what he saw was that if you multiply delta S of the universe by negative T, you're going to get like a type of a constant. And he called this as, well, what was ended up turning out to be the Gibbs Free Energy, delta G. Now, delta G is a really cool thing for chemists. And if you use delta G instead of negative T delta S, you have delta G equals delta H minus T delta S. And this is probably the premier equation of all of chemistry, because instead of thinking about weird negative delta H over T or something like that, these delta G values have been tabulated. And when I talk about thumbs up, thumbs down, reactions occurring, reactions are not occurring, we're going to look directly at delta G for these different values. And delta G will allow us to see if the reaction will occur or if it will not occur. And in this equation, this is the delta H of products minus delta H of reactant stuff we started this lecture off. So it's explicitly in there. The value of enthalpy is really high in chemistry, and that's the way to find it. This is the delta S of entropy, so entropy of products minus entropy of reactants. That number is multiplied by negative T, and you'll add these things through together to get delta G. Now, this is important because delta G is my thumbs up and thumbs down, all right? It's related to delta S of the universe, a little bit of a change, but if delta G says, yeah, let's let this reaction go, I would argue it's gonna go. On the other hand, you get a delta G which says no way, those reactions are gonna be really hard. And why chemists like this is it shows the two forces which go into delta G explicitly. Delta H has been our friend quote-unquote friend, since Chem 221, all right? We've used it to figure out when things are endothermic, exothermic. That's what it is right there. And delta S, which is calculated in a very similar manner, goes right there. And we're gonna see that delta S and delta H, they fight, all right? And sometimes they both want a reaction to go, and sometimes they don't want a reaction to go. And once in a while, like delta H says, I want the reaction to go, and delta S says, no, I don't want the reaction to go. So they kind of fight each other. The two-headed snake is what I always think about in this one. Because one part of the snake, all right, sound effects not necessary, sorry, yes, I am doing now. So the one like kills the other one, and that dominates the reaction, and we'll see how they can kind of compete for each other. So sometimes I literally do think about this as a two-headed snake, and the snake says, are you going to do this or not? And the two sides of the snake have to fight it out, and we'll see what kind of things influence the two snakes, making them stronger and weaker. All right, getting too excited here, but really all the reactions I have ever done in chemistry and all the reactions you've ever done in chemistry are dictated by this delta G. All right, that's literally what it comes down to, so. All right, so the free energy change, the delta G, which is something referred to as free energy, Gibbs free energy, Gibbs energy, all the same thing. It's the total change for the system minus the energy lost in disordering the system. That's what that part is right here. If you have an exothermic reaction, all right, then that means your delta H is going to be negative. And if you also have an entropy increase in the system, so your delta S here value would be positive, however, then you multiply it by negative T. Notice that if you have both of these, you're always going to get a delta G which is negative. So exothermic means delta H is negative. Entropy increase means delta S is positive, but you multiply it by negative T. Both of these are going to be negative terms. That's going to make delta G negative. So unlike the entropy of the universe, if a reaction is going to go, then the delta G is going to be a negative value. So in chemistry, we look for negative delta Gs. And if you have negative delta G, that means your reaction is going to go. It's spontaneous. It's product favorite. All these kind of terms we've been throwing around. That's if your delta G is negative. On the other hand, if you have an endothermic reaction, energy has to be applied to the reaction, then delta H here is going to be positive. And if your entropy is decreasing, you're cleaning your room, all right, you're putting all the chemicals back in the bottle that you spilled or whatever, that's going to make delta S here a negative, and that times a negative will make this positive. Both of those parts will be positive. So in these cases, your delta G will be a positive number. And delta Gs that are positives are not spontaneous. They're reactant favored. You might have a little bit of product, but it's not going to be anywhere near what would happen if you had a negative delta G. So delta G negative, reaction's gonna go. Delta G positive, reaction's not going to go, or at least not to a very large extent. So, this is a way that you can calculate if a reaction is going to occur or not. Now, this is a reaction where you can take some magnesium, add it to oxygen, and make MgO. If you've ever used like a flare sometimes outside and stuff, they use these really bright magnesium things and stuff. This is what's actually going to happen. Now, notice in this case, we have a negative delta H and a negative delta S. So what we want to do is we want to put these values into the appropriate spots. 25 Celsius we'll need to convert to Kelvin. What do we add to 25 to make it Kelvin? 273, right on. We're going to do a lot of that. Remember, in calculations, it's almost always about Kelvin. Also, one more thing. Notice how delta H, which is very common, is listed here in kilojoules, but your S here is in joules. If the final answer is kilojoules, which you can see from the first four meaningful numbers right here, you've got to turn this number into kilojoules. If we do that, do we take this number, do we divide by 1,000 to turn it into kilojoules, or do we multiply by 1,000? Divide, good. You want to divide by 1,000 to turn it into kilojoules. This would be minus 0.10836 kilojoules. So this number goes right into there. Divide this by 1,000 and multiply by 298. If you do all this, delta G comes out to be negative 568.9 kilojoules per mole. If delta G is negative, would we expect magnesium and oxygen to react to make magnesium oxide? Yes, that's right. Anytime you see a negative delta G answer, that reaction, thumbs up. That reaction is going to go. It's spontaneous, it's product favored, all these kind of terms. On the other hand, if you see a positive delta G, those are the reactions which are not going to go, thumbs down, non-spontaneous, reactant favored. Oh, I get shivers there. Anyway, I have problems with caffeine though too. Anyway, questions on any of this?
So, free energy is negative, correct, right?
That's right, that's right. The delta G is the Gibbs part, all right, which is also called free energy. Your delta G is this number, negative, and that's important, Tigran, because it shows that this reaction is going to go. Good, Rihanna. Cool. What temperature do you think we're going to use in the equation? Kelvin, yeah. Brianna, in these sections, always use Kelvin temperatures. So turn 25 to 298 by adding by 273. So Brianna brings up a really good point. A lot of times in lab, like we'll record Celsius, but in the equations, make sure you use Kelvin. Good question. Other questions? These are good questions. Okay. So again, when you're doing these kind of things, usually delta H is in kilojoules and usually delta S is in joules. Make sure you convert one to the other. In this case, I would turn the joules into kilojoules, but you could do it the other way. And the other way, which Brianna said, which is really important, temperature needs to be in Kelvin. So Celsius plus 273, like Serge said, would be the way to find the Kelvin values. Good. Kelvin scale is always positive. If you use Celsius, you have the chance of having zeros and negatives and stuff. So, other questions? Now, here's an overview of the 4 different possibilities you can run into using this equation. And you can see on the far right side here, there's 4 possibilities. Product favored means reaction's going to go, all right? So what if you have an exothermic delta H and your entropy is increasing in the system, your delta G, regardless of temperature, is always going to be negative. So these reactions are always going to go product favored. We're going to see something happen. On the other hand, if you have an endothermic reaction, energy needs to be applied to make it happen, and your entropy is actually decreasing for the system, which means it's becoming more ordered, then those conditions, you're always going to have a positive delta G. And those, at the very least, will be very reactant-favored Ks. They're not as likely to occur. These won't be very exciting. And the last 2 down here are kind of interesting combinations. These last 2 are where the 2 heads of the snake are fighting, all right? In the first case here, an exothermic delta H, if delta H is negative, it contributes to a negative delta G, which is what we want. So exothermic, it means enthalpy wants the reaction to go. On the other hand, a decrease in order means you're getting more organized, you're cleaning your room up. These kind of reactions don't want the reaction to go. You don't want a decrease in entropy, you want an increase. So if you have these 2 kind of conditions, then it's harder to say what's going to happen. And that's why Brianna's question was so important, because there's going to be some temperatures at which these reactions will occur, and some reactions at which these reactions won't occur. If the temperature is high enough, entropy, T delta S, is able to overpower delta H, the reaction won't occur. This is the opposite of what we just talked about. In this last set of conditions, the entropy, the disorder is increasing of your system, and entropy wants this reaction to go. On the other hand, endothermic reactions are harder to get going. They need energy. Enthalpy says, no, I don't think so. So these are also where the things are fighting, and the temperature will be a big player. Notice if you have both negative delta H and delta S, or both positive delta H, delta S, that's when you're going to get into temperature-dependent conditions and stuff. And we'll talk about how you can figure out the temperature at which it goes from not happening to happening, or vice versa. Questions? Sorry about the overdo right here. Ignore this part. A given reaction has a negative enthalpy and a negative entropy, which can be said about those reactions. So now notice first of all that both enthalpy and entropy are negative, all right? And if you have both enthalpy and entropy the same, this is where you're going to get into one of the conditions that temperature is going to play a big factor. So it's not going to be product favored at all temperatures. It's also not going to be product favored at any temperature. It's going to be one of these in the middle. So right away, because they're both negative, we can say it's going to be one of the temperature ones. If they were both positive, that would be the other set where you'd have a temperature dependent one. Now, if enthalpy is negative and entropy is negative, which one of those wants the reaction to occur? Like, which one is going to contribute to a negative delta G mathematically? Good. The enthalpy. Good. That's right. If enthalpy is negative, negative delta H is going to add to a negative delta G. So negative delta H's are exothermic. Those want the reaction to occur. But a negative delta S is not going to want this reaction to occur. That's a decrease in entropy. And a negative T times a negative delta S is going to give an overall positive value. And positive values do not make delta G negative. Entropy here is going to be fighting. If temperature is high enough, then T delta S will be more positive than delta H is negative. So at higher temperatures, and again, sorry about the overlap here. I need to work on my slides, obviously. I rewrote them a lot. Gonna be so cool, and wow, it sure failed on that. So sorry. Anyway, the higher temperature ones are going to be the reactant favored. Entropy is contributing towards it. So the answer here is C. All right. The lower temperatures, enthalpy is able to overpower entropy. The enthalpy term wants the reaction to go, and if negative T delta S is smaller than delta H, that's going to make delta G a negative number. But as the temperature gets higher, and again, Kelvin temperatures, like Brianna said, if the temperature gets high enough, then this part will overpower this part and become positive. So this would be a low temperature favored condition. Any questions? This is actually something that's really helpful in industry, because sometimes you'll have a reaction where one will be, say, enthalpy will be negative, but entropy would be negative too. And if you want the reaction to go, sometimes changing temperatures will allow the reaction to occur when it wouldn't normally. We'll talk about that here pretty soon. Okay. There are two ways to calculate delta G values. And the main way that's used a lot of times is you'll have delta H and delta S values. You'll know the temperature. You throw it into the Gibbs equation, and you can find delta G that way. But because delta G is used so much by chemists, you can also use the delta G of the products minus the delta G of reactants if you have them. And in the table for problem set 5, there's an enthalpy part, delta H, there's an entropy column, delta S, and there's also a delta G value. And if you have all the delta G's of products minus delta G's of reactants, that's a really nice way to do it, because you don't have to go through the individual pieces. Both of these ways work really well. Excuse me. We'll talk about other ways to find delta G probably Monday or so. Any questions on this? All right, this is a good place to stop. Have a wonderful day. We'll take this up on Monday.